a hole, but a hole does not prevent this field to be conservative. So be always very careful about how to use these theorems. I just remind you here what is the logic of the theorem that we proved today. Okay. Okay, I leave it very small. Of the not proven, of the stated theorems in the case of planar fields. Okay, go to black and go to 20. First, conservative. So let me see whether I'm able to do that. No. It does not obey. Because it does not obey on what is major. Okay. Conservative implies irrotational. And so this is the arrow. I'm not able to do it with my keyboard. Okay? Conservative implies irrotational. 2. Irrotational no dot here. Okay, he makes a dot. Does not imply conservative. Okay, so does not imply conservative. 3. Irrotational. And defined on a domain without holes, this implies conservative. Okay. Four. Conservative does not imply that it is defined on a domain without holes. Okay, so this you have to keep in mind very well. So homework. Homework. So you have to read, understand, and remember points from 1 to 4. Okay, in particular for negative points, for points 2 and 4, learn and remember example that prevents the logical implication to hold. What does it mean? It means that for point 2, You must know an example of irrotational field that is not conservative, the one that we gave in the last lecture and we discussed today too. And for the fourth example in which you have a conservative field, but it is the final domain with holes. Okay? And another homework, which is important too from a critical point of view, I ask you to think of it, and then if you want we can discuss together, but also if you don't want, we will do it. Find a potential for the conservative field. The one we discussed. Find a potential for the conservative field F equal to x divided x squared plus y squared, I enlarge a bit, and then y divided by x squared plus y squared. Okay, find a potential for that. You know that it is conservative. Second, which is very subtle, second homework, try to find a potential for the non-conservative field. And you know what is the problem? F equal to minus y x squared plus y squared, and x divided by x squared plus y squared. And most importantly, and figure out which is the problem and fight with it, discuss with it. Okay, this is very important to understand. So another remark I want to tell you is the following, and so we had here red. So another remark. Okay, it is not red. Is the following: the conservative field of the first homework, the conservative field given today is, so the correct word is radial, which means at every point it is directed like the vector r, which is equal to x, y. This is r. Okay, indeed, you have f is equal to x divided x squared plus y squared, y, x squared plus y squared. So this is 1 over x squared plus y squared xy. So it is r divided x squared plus y squared. It is a factor times the vector r, even though the factor contains x and y. So it is a function. The factor is a function, but it is good. There is no problem. So such fields are always conservative. This is another important thing to know. And such fields such fields are always conservative, provided that, this is often forgotten in books, provided that at every point their absolute value, their modulus, is a function of the modulus of R. This is true also in physics for the gravitational fields and so on and so on. Okay, so when you see a field like that, you immediately know that it is conservative, and for what concerns the modulus, here you have that modulus of f is the modulus of r divided by x squared plus y squared, which means modulus of r divided by the modulus of r to the squared. So this is 1 over the modulus of r, which is always written as a notation like 1 over r. Okay, so in this case you have conservativity, and this is very important in physics. So the last thing I want to do, this could be a very long, this could be a course, because from here we can open a field of mathematics, very interesting and very beautiful, probably much more beautiful than taking derivatives and computing integrals and so on. But we cannot, But what I cannot avoid telling you in this case is extensions to 3 dimensions. So now all results immediately extend to the 3-dimensional case, to the 3-dimensional fields. But the only thing that we have to say, we have to specify what is a hole. To specify what is a hole in 3 dimensions. So the point is always the same. The principle is, again, that you must be able to do what? To shrink any circuit, any closed curve, without exiting the domain. This is a property of the domain. Okay? So for instance, if you, example, in 3 dimensions, the domain, this domain here, R3, minus the origin, the 3-dimensional origin, gives no problem. This is quite surprising, perhaps, but why? Because this time you are in 3 dimensions. Hope this is not good. You are in 3 dimensions, and suppose that here the origin is not in your domain. But in 3 dimensions, when you draw a circuit, even though it is very complicated, you don't have an interior part. You are in 3 dimensions. So you can lower or you can pull your circuit toward the high, and then avoid the point. If you are missing only one point, there is no problem. You can shrink your circuit up to a point without meeting the missing point. You go a bit higher or a bit lower. This is not a problem. You see it, try to figure out. Try to see it. If you don't see it, just stop and try in your mind and to discuss and do it with a pencil and so what happens and see what happens. So in order to prevent some circuits to be shrinked up to a point without exiting the domain, you must have a domain not without a single point, but without a whole line or whole curve. So on the other hand, the domain, which is, for instance, R3 minus the z-axis, so x equal to 0 and y equal to 0. So this time what you cancel from your domain are the all points of the z-axis. So the z-axis is missing here. It's not there. All other points are there, but not the point of the z-axis. And now you see, you consider a circuit C embracing the z-axis, and so it is not possible to shrink this circuit without crossing the z-axis. And this is the generalization to 3 dimensions of the property of having holes in 2 dimensions. So the name of this property, so I write it down in order to make this guy readable to you. So every circuit enclosing the z-axis cannot be shrunk to a point without crossing the z-axis, so exiting the domain. Notice that this is not a property of the field, it is a property of the domain. Okay? In mathematical language, the property of shrinking curves up to a point without exiting the domain. The property, this is a property of the domain, of domains, is called it is a strange word, but it's called simple connectedness. Okay? So it is just a word, but the principle is that. So let me just copy. This is the last thing I want to do today. Here you have a copy. We did not copy anything, so eliminate. Let me try again to copy this guy here. It must be possible to copy it. So we try duplicate. Oh no. Oh no. again, eliminate. How can do copy? Copy as a picture probably, but it's a style, convert in text. Let me try to convert in text. Ooh, nice, but this is not what I wanted. Okay, try to do that. No, everything is wrong. However, okay, I will do it by hand. Something very bad happened. Okay, I do it by hand. So first, okay, conservative implies irrotational. Okay, now it has learned. Irrotational, okay, I put the arrow at the end. Irrotational does not imply conservative. 3. Irrotational and defined on a simply connected domain implies conservative. At the end, conservative does not imply defined on a simply connected domain. Okay, so conservative implies irrotational. This is true. Irrotational does not imply conservative. I know I'm boring, but I want to repeat it many times so you learn it. Irrotational defined on a simply connected domain, so a domain where it is possible to shrink every circuit without exiting the domain, implies conservative. 4. Conservative does not imply defined on a simply connected domain. This lecture was very long and very conceptual. The letter perhaps is not very beautiful, but the matter here is very beautiful. So if I was not able to see the beauty, try to do it by yourself. I will prepare some question on that in order that you can do some exercise. And so next time we will move a step forward. I will start giving you some theorems that put some order in all these matters. Okay, not only words but theorems, because we live at that. Okay, thank you very much, and I hope that this recording is effective, has been effective. See you.